today we are going to discuss a brief introduction of the chapter Real Numbers. So here we are going to see a very small overview of this chapter today. So overall we have discussed different types of numbers like decimals, integers, rational numbers and irrational numbers. And we know that all these numbers together comprise real numbers, and we will continue our discussion on real numbers in this chapter. Now we will begin with two very important properties of positive integers. So these properties are namely the Euclid's division algorithm and the fundamental theorem of arithmetic. These are two new properties which we are going to look through in this chapter, and today we are just going to go through these properties very briefly, and we are going to see what these mean and try to get to know what these properties are for. So first of all, we are going to discuss Euclid's division algorithm. So as the name suggests, this algorithm has to do with the divisibility of integers. It states any positive integer a can be divided by another positive integer b in such a way that it leaves a remainder r that is smaller than b. So if we put it in simpler words, this algorithm is nothing but the usual long division process. It's just a different way to state this process. And this result has many applications. Mainly, we're going to use this to compute the HCF of two positive integers, and we're going to look to it. We're going to discuss it more briefly in more lectures, other videos. So don't worry about that. Today we're just going to give a brief about this algorithm. So moving on, we have the fundamental theorem of arithmetic. Now from the name we can infer that it has something to do with the multiplication of positive integers. So every composite number can be expressed as a product of primes in a unique way. This important fact is the fundamental theorem of arithmetic. So basically we can express any composite number as a product of primes in a unique way. So this is nothing, just a simple statement, and we are going to see this in detail later on. It has some very deep and significant applications in the field of mathematics. So we are going to look at some of the main applications this theorem has. Let's see. First, we use it to prove the irrationality of many of the numbers such as root 2, etc. So you're going to come across various types of questions in which you're going to have to prove that these numbers are indeed irrational numbers. So there we're going to use this theorem. Second, we apply this theorem to explore the nature of decimal expansion of a rational number like p by q. So what this means, so basically rational numbers have different types of decimal expansions. Some decimal expansions are terminating and some are non-terminating. We're going to discuss about it in detail. So when the decimal expansion of a rational number p by q, where q is not equal to 0, is terminating, and when it is non-terminating, repeating. So we can use this theorem and determine whenever the rational number has a terminating decimal expansion and whenever it has a non-terminating repeating decimal expansion. So guys, I hope that you got a brief about these two things today, and I hope that you're going to understand this in a more better way. It was just an introduction to these two topics. We're going to discuss these in detail. So thank you for watching today.